we start to move on with the second talk of today, Professor Ronald Lawler. So if you are in the photo-kidnap field, you are familiar with the name. Professor Lawler discovered the kidnap effect, not the photo-kidnap, the kidnap effect in 1967, alongside with Ward, Bargon, and Fisher, who were in another group at the time. And today is going to speak to us about maybe the past, present, and what you see for the future a bit as well of Photo-Kidnap. So yeah, the floor is yours, Ron, and very much looking forward to your talk.
Okay, let me see if I can find it. Okay, can you see it?
Yes, maybe you need to put it in presenter mode.
Let's see.
Yeah.
How is that?
Not good.
Okay, let me
maybe come back or play from start. If you do maybe play from start, I think it's.
I think I'm just going to do that. Yeah, that's the simplest thing. Okay, how about that?
Yeah. All right. Yeah, it's right. Perfect. Yeah, thanks a lot.
Fine. Okay. Yeah. Well, I'm very pleased to have been invited to participate in this. I want to tell you a story today. This is quite different from the other presentations, of course, about an experience that, if you're lucky, you have once in your lifetime as a scientist, which I was fortunate enough to be involved in by accident, actually, some time ago. So let me start out by sort of setting the stage here. This did happen, as Felix said, in 1967. And it's interesting to think about what the situation was as far as science in 1967. That was 58 years ago. And if you think, for example, 58 years before 1967 was 1909. And so listening to me talk to you about something that happened in 1967 would have been sort of like me in 1967 hearing somebody talk about a new concept of pH, or one of Rutherford's co-workers talking about that they now knew that alpha particles were doubly charged helium. So this is a long time ago. And it's interesting to think about what the situation was as far as doing science and as far as communication. And here's just a list. By the way, I want to mention that I'm in the process of putting together a bibliography which will give references to a lot of the specific work that I'm talking about here too, because I think this is something that many of you, especially students, may not have been looking at, and also it means that you don't have to take a lot of notes or try to follow that. And also, this will be recorded, so I'm going to go through this fairly quickly. If you look at this list, the things we take for granted now, email, smartphones, and so forth, even making phone calls overseas was difficult. There really were no commercial lasers, at least ones that had the power and the wavelength that you could use for Photo-CIDNP, for example. So you used high pressure mercury lamps usually for photolysis. But you did have airmail, you had good libraries, you had journal publication with a small number of months delay, and you had meetings and symposia. So how did we communicate? If you had research which was going on that you wanted other people to know before it was published, what did you do? Well, you could always write. You could mail a letter. And written correspondence is something that you did. A lot of us set up actually mailing lists, so we would send preprints of manuscripts before they were published. But also there were gatherings that you could get together. For example, Gordon Research Conferences, and that's where this all started. There was a Gordon Research Conference in 1967, actually about 40 miles from where I live now, at the Kimball Union Academy, on magnetic resonance. This was the second magnetic resonance conference I had been to after I joined the faculty at Brown after being a postdoc for George Frankel, who was actually one of the two chairs of this Gordon conference. And there was a lot of excitement. The exciting thing there that people were more interested in was the fact that pneumatic liquid crystals were being used to reveal some of the dipolar interactions, which could give you structure, which otherwise is very difficult to do. And this is before Waugh, for example, had figured out how to do some high resolution work in solids. But there was also a paper by Hans Fischer. He was then in the Polymer Institute in Darmstadt in Germany. And he had done some very nice work on finding coupling constants of small alkyl radicals in reactive media with OH radical abstraction and other things. And he was scheduled to give a talk, which was very nice. But at the last minute, he contacted the chair of the session, who was Phil Rieger, one of my colleagues at Brown who did ESR, and changed the title of his talk. And here is in my writing from the program, I found that in my files, his new talk was called NMR Emission from Molecules Formed in Free Radical Reactions. And what he showed was a spectrum. And this was of decomposing benzoyl peroxide in a cyclohexanone solvent that was allowed for radical hydrogen atom abstraction. And he saw this emission signal. As it turned out, it was from benzene, and it came and it went over a fairly long period of time. Here, in fact, is his student Bargon, Joe Bargon, who was really the one who discovered this and had a time trying to persuade Hans that this was real. Here they are at the spectrometer, and here's Joe, and here's Hans. Joe has actually provided a very nice memoir, of a personal description of how this discovery came about in Darmstadt. I'll give you the specific reference to this. This was a memorial issue of Helvetica for Hans Fischer, who passed away about that year. But they published the paper, and in fact, if you look at I don't know whether I can do this. Yeah, here. If you look when this manuscript was submitted, it was about a week before the Gordon Conference, so they had already submitted this. And what Hans had showed in that paper, as well as in the seminar that he gave at the Gordon Conference, was an explanation for this effect. And the explanation basically was what we now would call the Overhauser model, or dynamic nuclear polarization, which Carl Hauser and Rex Richards had actually been, among others, had been looking at for some time in solids and liquids, but with stable radicals and other kinds of things. It was basically the Overhauser effect. The idea being, oops, sorry, I'm going to have, my mouse is kind of sensitive. The idea being that radicals were formed with equal population in the electron spin states, and that then by selective relaxation could induce a nuclear polarization. And that was a very reasonable explanation. And you could estimate, in fact, from the interactions in the radical, how fast these interactions would be. So I went back to Brown after this conference, and I had an office next to my friend and longtime colleague, Harold Ward, whom I had known when he was a postdoc and I was a graduate student at Berkeley with Andy Streitweiser. Harold was a physical organic chemist, and he was at that time starting to do some ultraviolet photochemistry. But in addition, he was finishing up some work that he'd done as a postdoc elsewhere, actually at Oxford, in acetylene chemistry. And one of the things he did was try to monitor the cyclization of an acetylene by an anionic cyclization. And the way he wanted to make the anion was by a halogen metal exchange with the lithium compound. And I said, hey, Harold, what have you been up to? And he said, well, we wanted to follow this by NMR and ran a spectrum. And he said, he got a really strong spectrum. This is the first spectrum he got. He said, if you look here, while this reaction was going on, we got these negative peaks here. And we don't know. And we ran at another time, and they sort of were there. and we don't know what's going on. And I said, well, you know, I just heard something like this at a Gordon conference. And so I told him about Hans's work. This is the actual reaction he was taking place. And the idea was to put a lithium here, but instead there was another reaction going on, and this is a blow up of that. And you can see there's even a hint of some emission here, and these look like they're a little enhanced. The one on the bottom is actually, this is butene mostly, but it's also got peaks from the alkene that it would be formed from the terminal methylene here, involving the terminal groups in the acetylene. So I told him about Hans's work, and he immediately wrote a letter to Hans. Of course, there were no phone calls, there's no internet or anything, and I told him about this. Hans very graciously wrote back and said yes, that they had prepared this for publication and submitted it, and that they would be happy to share their manuscript with us. And please tell us more about what you've been doing. Well, it looked like this was something we really need to look into. We were just junior faculty at Brown, and we wanted to find something interesting to do. So one night we actually got together, and just about every alkyl lithium and every alkyl halide we could find in the chemistry department, in refrigerators in the stockroom, every time we mixed these together, we got something that looked like this. And we went home a little stunned because we knew we had really discovered something we needed to look into. So what we found was, and this is Harold, and this is us doing the experiments, although this was when Bob Cooper, graduate student, was there. This is Harold preparing the sample, me timing it here. Normally I would have been running the spectrometer. This is an A60A spectrometer, which is, you know, this was one of the first, this was really the first routine NMR, which we had only had for a year or so at Brown. So this is how we ran the experiments. So we published a paper about, it came out a little bit after Hans's. We submitted it. You can see not too much after the Gordon conference. And this, for example, would be a spectrum from N-butyl bromide and N-butyl lithium. So the two alkyl groups are the same in that case. And you can see there's a fairly decent spectrum. This is an A60A. This is 60 megahertz, just ordinary CW field sweep instrument. So we had all of these. And there were we found a lot of other examples. And so what we did was, and also others who were starting to get involved in this, was start classifying the spectra with what we call the phase of the enhanced peaks. For example, when you had a sample like Fisher's, we called this the net effect, and it was either an emission or enhanced absorption. What we were observing ended up being called the multiplet effect, and where the either EA or AE, depending on whether the downfield peaks in a multiplet were wait a minute, I needed, sorry. It's very annoying. Let me see if I get it. Yeah, where the downfield peaks were E and the upfield peaks were A. So he sort of had this classification we could look at for different kinds of spectra, and other people were starting to get involved in this too. And there were some other subtle things. This is our spectrum, but in the footnote of our first paper, and we never really looked much at it, what we found is that depending on what you add to the spectrum, add to the sample, you could actually find an inversion of all of these peaks. In other words, instead of AE, you got EA, you got AE. And as it turns out, probably this was from radical pairs that had escaped and formed new radical pairs from random encounters. So there's some indication. Rob Kaptein got involved in this by extending fairly quickly the work that Fisher had done, although Bargon, I think, had also by then started to extend it to a lot of alkyl radical situations. What he found was there was also this inversion of phase. And that was coming from a product where there was chlorine abstraction taking place. Well, there was another aspect of this that I eventually worked out, which was the populations corresponding to this. And if you did this analysis, and this is styrene, which was an easier spin system to analyze, what you found was that in this particular case, the upper and lower states were overpopulated relative to the middle. Or another way of putting it, the ones in the middle were underpopulated. So the question is, it looked like products with lower total nuclear spin are formed in lower yield. Well, you put all of this together, and the first person who really published on this was Gerhard Claus, who had been thinking about triplet states and all kinds of things for a long time. And he proposed a model. It was a little bit like the Overhauser model, actually, but it was involved the triplet state levels rather than the doublet state of the free radical, and had did a quantum mechanical analysis of this, in which you had interactions of the electrons and nuclei with this field and so forth, and you also had hyperfine coupling and electron-electron interaction and other interactions, and worked out a model which was basically a relaxation model. It was like in a sense like the DNP model, except that there was a modulation of the singlet triplet transition here by sort of turning off and on the hyperfine interaction, the effects of the hyperfine interaction as the pairs separated and came back together. It's not surprising that he had this picture, because he talked to Sam Weissman about it, who was one of the grand old people of magnetic resonance, who had thought a lot about relaxation. The important thing of this was here was actually a formula for the transition probabilities relating to the hyperfine splittings and the lifetime of the pair and some other parameters. Well, not too much after that, we discovered that Rob Kapteyn and Lutz and Osterhoff had also been thinking about this. They had used basically the same Hamiltonian. They had single triplet mixing, but it was a more quantum mechanical treatment, in which basically what they were talking about was how the nuclear spins caused interactions between the singlet and the triplet state, an oscillating effect. And they also ended up with a formula for the singlet character, which would be related to the reactivity. Well, there were a few diagrams involved in these early ones, and so Harold and I actually were invited to submit a paper to Accounts of Chemical Research, and we ended up with two, because we had too long a paper initially. And what we did was put in some diagrams which sort of showed this. You can look at them here, but they're familiar now, in which you have the attraction for a reaction and the repulsion of the triplet, which everybody thinks about now. And what the two different models that we had seen, Claus's and Kapteyn-Osterhoff, was how the interaction here, this is the spacing between the levels that are mixed here, happens as the radical moves around. And in Claus's case, it was moving up and down here and shutting things off up here, shutting off the singlet triplets. In the Kapteyn-Osterhoff picture, there was a sort of a constant J. It oscillated a while for the singlet character, and when it reacted, the singlet part reacted. What we suggested, and I guess I suggested, was a model for the mixing of the singlet and triplet, which was a vector model. And I think this may have been the first time that this appeared in terms of the CIDNP theory, but because I don't remember seeing it anywhere else. But it's certainly not the first time anybody ever used this picture. In fact, Ryan Druckelhorst, about the same time, has used it for understanding some magnetic field effects. I also tried to put this model, which was implied by Claus and Kapteyn-Osterhoff, into some rules involving the magnetic fields seen by the electron, which involves a G factor, hyperfine splitting signs, and so forth, in this rather incomprehensible table. Well, at about the same time, Rob Kapteyn had been thinking about this, and he came up with a very nice formulation of this, which are now called the Kapteyn rules. And it's a very, very nice way of relating what you see, whether or not what we've called the phase, whether it's plus or minus or EA or AE, to some very interesting parameters, hyperfine splittings, G factors. Okay, well, when you've got something where you've got observations and you've got a good theory, what do? You have a meeting. Well, this was a meeting which was actually held a little bit before or I guess it was a little after the meeting where the radical pair theory had been formulated, and this was held in Houston, Texas. Fisher and Art Lepley and Mike Cochavira were the ones who started this, and it was actually a little international. Rob Kaptein was there, of course. Hans Fischer was there, and very interestingly, Fritz Gerhardt, who had worked for Schultkopf at Göttingen, was there. He talked to almost no one. He came, he gave a talk, and went back. And I'm going to give you a reference to a paper he wrote at about this time, which was basically the same. It had some of the same elements as as what is now being called the CKO theory, the Kaptein or the Claus-Kaptein Osterhoff theory. So this was the first meeting, and actually the two papers here with Cochavira and Trizzolo came from Bell Labs, and these were all in what we would now sort of call Photo-CIDNP, because they were using light to excite things. So anyway, that was the first symposium. There was another symposium in Brussels the next year. Then there was one after that in Tallinn, in Estonia, and what these really brought in the international community in a big way. So I wanted to just now go strictly through a sort of summary of sort of where the things stood before the radical pair theory was developed. The papers were published in 1969. And these are the reactions that had been studied before then, and they were studied really qualitatively. Most people really just used the information to indicate that there were radicals or other paramagnetic states as evidence for that. Well, you can see there are a variety of reactions here, including Claus, a beautiful set of papers by Gerhard Claus. Which actually showed, I think, for about the first time that singlet and triplet born pairs led to different chemistry. So those are the reactions. Another question is, where was this done and what kind of instruments were involved? Well, these are the same set of investigators. When you look at this list quickly, all you see are variant instruments. And which is very interesting, because these are not just from here. In fact, Anatoly Buchachenko had access to a variant 60 megahertz instrument in the USSR and published a paper in 1968, which is on the benzoyl peroxide. So these were the instruments that were used, and these are the places. And you can see Germany, Netherlands, USA, and the Soviet Union. And I wanted to add these were a little after the radical pair theory, so they were a little later. Hira and Maruyama in Japan actually also did some of the early work in this, but there was a JEOL instrument that was used, and that's the only one I could find in this very early work other than a variant instrument. So conclusion is, early CIDNP was reported from 12 institutions, 5 countries using variant instruments, but the Brooker instruments made the current FT era possible because variant basically got out of the business. So I'm going to go fairly quickly through the rest of this, but what I want to do is just talk about a little bit about the radical pair part of this. There were some variations about the same time. Claus and Osterhoff had these. Cy Glarum came up with an idea which was related to this level crossing at about the same time. Hans Fischer also published a paper similar to Glarum's, talking about which differed a little bit. These were all in the way that you dealt with the interaction between the electrons and the reaction. And Gerhardt had one which was a little bit like like Claus's, which had some other aspects to it. And then Frank Adrian actually showed that you could combine the radical pair model with with electron spin polarization and DNP later. So what's the precedent for this? Well, turns out everybody at this conference, Gordon Conference, should have known about this paper. Some did, but everybody forgot it. This is a paper about electron polarization by Dick Fessenden. This was during radiolysis. It's a beautiful paper. And this is a rather strange second derivative spectrum, ESR spectrum. But the lower field hydrogen atom line is an emission, and the upper is enhanced absorption. And nobody ever explained this, and it kind of dropped away because there were all these other wonderful results that people were interested in. So this is the first example of what we call chemically induced dynamic nuclear polarization, CIDNP. So there are various other things that were done. One of the things is that there were some problems with lifetimes. Frank Adrian and Rob Kaptein found that if you include re-encounters, it stretches out the lifetime of the radical. There's a triplet Overhauser mechanism, which was developed over a period of time, partly with Peter Atkins at Oxford, which was a way of just another mechanism for CIDEP, which could then do cross polarization with nuclear spin systems. And then there are a lot of precedents, which I won't really go through say, but it turns out that if you go back, the idea of magnetic fields influencing spin states, it goes back a long ways. And I'll give you references in this bibliography to this. It goes all the way back to Wigner, who used basically this model to describe orthopara hydrogen conversion. And so there are a number of these that I could show you. But okay, so how much did people pay attention to these things? Well, one of the things you can do nowadays with Google Scholar is actually do a search, a keyword search, and and they will come up with a number of with specific publications as well as a combined number that are published during any period of time. And I actually did this for CIDNP being the key word, beginning in 1967 and actually continuing. But it's very interesting to look at this because here there were 3 publications in 1967. Turns out I think one of Fisher's publications may not have appeared yet, but and then we go up here, okay, and this is about when the radical pair model developed, and then there was this rapid climb here, and then it leveled off. And it's very interesting because if you extend this out to the present day, this is what it looks like. So we're up around here. This is the first 10 years here. This is going here, and it turns out that what happened is that CIDNP was not being mentioned very much, and part of it was because people who had been doing CIDNP now are doing other kinds of things. As most of you know, parahydrogen-induced polarization came along, and there were a lot of other things. But this is fairly characteristic of a field which starts out just suddenly from nothing, has an induction period, and then goes up to a maximum, levels off for a while everybody's sort of thinking up new things, and then just falls off gradually. It turns out this has been studied. It's the difference between pathological and normal science. Some of you may know, the older people may have recalled something called polywater, which was water with very strange properties, which some people could reproduce, but ultimately it turned out to not be a real phenomenon. And this is the publication record there. And in every place where this was done, it went up, but then it just really dropped off fast. So what the people who talk about this, pathological science goes up quickly and comes down quickly, whereas normal science does what we actually saw with CIDNP. So everybody rest assured, CIDNP turned out to be normal science. Okay, the last thing I want to do is show you a rather large flow chart, and I won't say very much about each of these. Again, I think what I will do is make a PDF file of these slides if you happen to want to look at them in more detail, or this is also being recorded. So what I'm going to talk about is sort of over on the left-hand side. It's roughly a timeline, but it's not exactly, okay? But what it is all the factors here and how they've been connected. Obviously, we started with a discovery, okay? And the discovery actually had three parts. When you think about it, there were experiments, obviously. There was theory, and actually even early on, there were applications because people were just using the appearance of the phenomena as evidence for free radicals. But then as time went on, all three of these areas really expanded. Experiments became big. FT-NMR got developed in the early 70s. We had pulsed excitation with lasers and some chopped light sources. Some people did that. The CIDEP began being investigated in more labs. It became a real phenomenon, not just something that happened in radiolysis. And related to this was something that had been around a long time, was optically detected magnetic resonance. There were some other examples of this later. So experiments, sort of the possibilities of experiments really expanded. In terms of theory, we've already talked about that really. There was a radical pair model, there's a DNP, and there's a triplet mechanism. The radical pair model is mostly what we find with the chemistry that everyone is doing now. But it turns out the triplet mechanism combined with DNP is not a bad way of also producing CIDNP effects. Applications, I guess one thing you could say is there are mechanisms involved, and the early ones were reaction mechanisms, basically. Later on, however, this was extended to more organic reactions. But then there's a field called spin chemistry, which is being used very broadly nowadays to include all of the rest of this stuff. But for me, spin chemistry goes back really to, in a sense, Anatoly Bochichenko and Nick Turo, and in the sort of late 70s, and something which it turns out that almost by accident I predicted in 1971 with a little paper presented at the Brussels conference, that there's an implication you ought to be able to detect these nuclear spin effects both by real magnetic field effects, ones that are well understood, and magnetic isotope effects. And Bochichenko has done a lot of work in both of these fields. The only area, though, that is really well defined here, where we know what we're looking at, is work that Nick Turo did and others on the and Anatoly on the photolysis of ketones. That's very well documented. So that's what I call spin chemistry right now, but it's a very, and then there's a lot of structure and dynamics work, which is where you guys come in. If, for example, this beautiful stuff started largely by Rob Kapteyn, I think, as you know. There's been very nice work done in photosynthesis, which meant that that solid state methods had to be developed. Radical pair dynamics have been connected with making the theory more understandable. And you can determine the signs and magnitudes of hyperfine splittings and things, which relate to a radical structure. Okay, so those are there. Now, another field that is developed is spin engineering, and one of the first people to look into this was Rob Kapteyn, with separating the multiplet effect from the net effect, which wasn't always easy. Another little secret of FT-NMR was that if you use 90-degree pulses on a spectrum showing multiplet effects, the multiplet effect disappeared. So usually you were confined to using lower angles, but there are other ways to get around that now because of spin. This is an enormous field that interacts with all the rest of these. Okay, hyperpolarization, that's the name of the game, right, for the webinar. And that goes down here. Finally, Photo-CIDNP showed up. Okay, you were wondering, huh? And part of this, of course, is parahydrogen-induced polarization. That both Joe Bargon and I played a sort of accidental role early at a Gordon conference in particular. Joe has expanded this enormously and done beautiful research. I sort of I published a couple of papers with Rich Eisenberg on this very early on. But this has been enormous. Simon Duckett has done beautiful work here. And dilution, dissolution DNP has turned out, DNP has come back, as you know, as sort of recovered, but with, for example, with electron spin radiation. And then finally, right now, there are 3 areas that are still pretty speculative about how this is all going to interact. Chiral induced spin selectivity is another one of these things that is just popped up. And it's really a way of making polarized electrons from a variety of samples that are chiral using polarized light and other methods. And that has a lot of possibilities even for doing cross relaxation. But basically, it's a way of getting, it's a way of getting, there we go. It's a way of getting electron polarization. Another thing which is still largely theoretical, golly, I'm sorry. It's largely theoretical, but it has been worked very heavily, especially by Peter Hora, is something goes back to a proposal that Klaus Schulten made, looking at the anisotropic interactions, hyperfine interactions, and thinking, well, there's probably a way that you could relate this, if you could identify radical pairs, to bird migration. And some of those, that chemistry is being worked out. And then finally, it's quantum computing, because when you think about it, that nuclear spins and electron spins spin up as a 0, well, let's say spins down as a 0, and spin up as a 1. And there's been a lot of interest in whether or not you can use things like radical pairs, which are polarized or interacting with each other in various ways, as a way of making quantum computers. And Mike Wasilewski has been very active in this area, and I'll give you some references to that too. So anyway, yeah, this is it's a big diagram, and I think each of you may know things here that you could add other lines and connect other fields. But this is what I have seen. So let me finish up then quickly. First of all, I think it's true to say that significant discoveries like this that define a new field are rare. They happen, I think, more frequently in fields like astronomy, where suddenly you see something in a star and there's no explanation. It's been really very interesting to watch this develop with CIDNP. The next thing is that, as I've mentioned here, in the case of CIDNP, they were made very quickly. There was communication among the people who in the different labs, but they were all using variant instruments. And in a sense, it's variant that was responsible for making CIDNP possible. And also, the early things were not done by people who did NMR. I mean, I did ESR actually when I first went to Brown as a postdoc. Harold Ward was an organic chemist. Fisher and Bargon were in a polymer institute, and Bargon was working on his PhD basically in polymer science. And so these early things, but we used the spectrometers for analysis, and out popped this effect. Just something to think about. And then when I didn't really go into the analyzing the theories, but there was a lot of ideas about how this could be explained for floating around, not just the DNP, because people were looking at these effects that I outlined, the net effect, the multiplet effect, the strange distribution of populations. And a lot of this came up. And the great thing about the work that Klaus and Kapteyn and Osterhoff did is that they actually made this quantitative, or at least semi-quantitative. It was a theory you could actually look at that started making predictions. And these predictions mostly turned out to be right. And that's where things really took off. And then once that happened, as you saw in that publication plot, once you had a good theory, and that the people started thinking about experiments, how to test the theory, and there are really creative applicants, which are continuing applications, which are certainly continuing today. And then finally, I want to say something about just the nature of how we were doing research then. Today, collaborative research, like in a sense, that's what we're doing here in this webinar, is a lot easier today and more common. And it has been now for quite a while, for a few decades, actually. 1967, it really wasn't. And one of the interesting things about this is that there was very little overlap among the research in the research groups. It wasn't that we were sort of friendly competitors, and it wasn't that we didn't communicate, because there was an exchange of preprints, and also we met at meetings, and eventually that our students, for example, began to become postdocs. And one of my students, for example, went to Oxford as a postdoc with Peter Atkins and did some very nice work with him on the theory of CIDEP. But this was not the same as having a lot of people working in either in different places or getting together in the same place the way it is today. Just to give you an idea, whoops, here, back again, sorry, but this is very delicate. About one of the last papers that I was involved in, with research I was involved in, which is now about a little more than 10 years ago, was on endofullerenes, and this involving things like with encapsulated hydrogen and water. It involved things like orthopara hydrogen conversion and water conversion. Interesting stuff. That paper had 22 authors from 8 different labs in 5 different countries. And that's, I think, is much more common now. It just would not have happened when we were first doing this. So things have changed a lot, and I think it's mostly for the better. So anyway, thank you. And if you have some questions, I would be happy to see what I could do.
Thank you, Ron, for this nice overview. This is really amazing to see the history and connected to the science. I think something that's really striking is what you mentioned, is the amount of simultaneousness of the discoveries in this field. And that's something you mentioned that at the end, but so what strikes me while we wait maybe for a couple of questions in the chat is the velocity and how simultaneous discovery were made and progress were made. And yeah, you seem to have a very collaborative mindset. I think you explained that by the non-overlapping maybe of the areas of research. Nowadays we have much more fierce competition, at least in our mindsets, in science. And maybe if you would have made this discovery in 2025 in this context, are there like maybe something you would have tried to do differently? Like, would you have been more protective? I don't know. How would you have approached this collaboration maybe in nowadays with because you mentioned that a lot, right? The internet, phones, being more communication being more easy, but as well competition being more fierce. What would be your thoughts about this?
Well,
and please others ask questions in the chat.
Sure, I could just mention this briefly. I think that it depended very much on who was doing the investigation. In fact, I could give an example of this, my last real involvement in research was for several years collaborating, actually from where I'm sitting right now in New Hampshire, with Nick Turo's group. Nick Turo, of course, is very well known for photochemistry, and did do a lot of Photo-CIDNP. Nick was someone who, regardless of when he did this, would collaborate. I think he was a perfect example of someone who just could not help involving everybody he thought might be interested in this. And that's one extreme, and that still exists today, but it depends very much on the investigator. I think one of the things that has happened, and you're sensitive to this, I think it's different from, let me back up even further. I think a lot of this, all of the early work was not done in a laboratory where patents were of interest. In fact, I don't think there were any real industrial laboratories involved in the initial part of this, or even somewhat later. And I think some of the competition is there just because of the business part of a lot of research nowadays. I think there's a much more of an emphasis. I don't want to say that it was easier to get funding in 1967. It certainly wasn't necessarily, but I think there was less justification you had to give that somehow this would lead to a product, or that this somehow would be of help to medical science. Not that those are bad things, but I think that the atmosphere has changed, and I think that may have affected the level of competition that you're talking about, Felix. That just wasn't there in the early days of CIDNP. All it mattered, there were personality things. I mean, in fact, when I think about especially Gerhard Klaas, who could be very generous, but he mellowed a lot as he got older, and he helped out a lot of younger science. He was very competitive. And I think that each of us felt that, well, it was a friendly competition in the sense that we in a way, we liked having the competition, because as I think that I used to tell the students, if you're working in a field where nobody is competing with you, you might think about whether or not your research is important. And in a way, it was really good to have these people breathing down your neck, because you knew what you were doing was important. So it's a long answer, but I think that depends. The answer really is it depends on the type of research and where it's being done.
Makes a lot of sense. If we don't have further questions, I think we can move on.